much of the time. So I don't need to worry about it? Or?
Yeah, and then make sure that we are standing like here so they can like see us, you know?
Okay.
Try our best. So, all right, everybody. Thank you very much for coming out tonight. We're very happy to hear that you clawed your way all the way here. Yeah. Okay. You know, I hope you didn't get too crabby. Oh man. Okay. Tough crowd. We have got a phenomenal workshop here for you guys. I know I'm a lobster, but please play along. And we're going to be going over our intro to machine learning and KNNs. I have two of our three lovely officers who are going to be presenting tonight. One of them is getting here late. And yeah, you kick us off.
All right. How we feeling about AI, y'all? Okay, that's what we like to hear. Yeah. Welcome to Beginner's Track. This is for the folks who I feel like everyone's heard of machine learning and AI, but what's up with that? That's what this track's for. So we're going to be covering that today, and pretty much we're just going to do a crash course on what machine learning is, and we're going to be diving into this concept called KNNs, which our fellow officer Venkat over here will introduce. But let's see here. Oh wait, do I need to do it on this slide? There we go. All right, so first things first, all of our announcements, all of our events for this club, we mainly send out through our Discord and our Instagram. So those are the links for that. This is normally where we put all our announcements for when our events are, when our meetings are, all the different workshops, because we run a lot of different stuff here at ACM AI. So feel free to take a photo of that or just take a little mental note. I'll give you a few seconds to go crazy. All right. Wait, can I? Oh, it's gotta be this one. All right. But you're probably thinking who are these people standing up here shouting at you? We're the workshop officers for this quarter for ACM AI, and we're gonna be holding your hand through how to learn machine learning and AI. So my name is Eric, and
I'm Venkat. That fun fact is very outdated. I do love Star Wars, and yeah, it's not outdated. It's not outdated.
I did get attacked by a monkey. I would talk about it, but you're here to learn AI, so we're gonna put that off to the side here. We got another officer who's running across campus right now from a class or something. His name's Gregor. He's going to be walking you through our hands-on demo today. So don't worry, you'll get to see all of our beautiful faces up here. But without further ado, let's talk about what's on today's agenda. Today's agenda is going to be like I said earlier, we're going to cover machine learning. We're going to do some KNNs. We're going to talk about what they are. And then after that, we're going to do a little fun demo, and then we'll call it a day. And yeah, that's kind of it. But before that, I actually lied. There's one thing, formalities. What is this club? Woo! All right. Okay. What even is this club? I bet a lot of you, how many, can I get a raise of hands of just hold up one if you're a first year? That's crazy. Okay. So we got a lot of first years. So you're probably thinking big campus, big club, what's the deal? Let's talk about it. So let's do a really quick formality intro. So we're ACM AI. Our mission, essentially, they put it in formal words up there, but we're pretty much just here to teach you AI. We're here to have a good time, learn about all aspects of it, the ethics, the function, the use, whatever. There's paragraphs and paragraphs of it. We don't really need to cover that. We're gonna cover the beginner's track, which, I said earlier, is pretty much just the introductory concepts and the introductory math that you need to do this. You don't need to know anything coming in here. We're really big on that. So even if you're maybe a history major and you're here, you should be chilling. Not that we were really expecting a lot of history majors, but whatever floats your boat, we're here for you. And if you want to break down essentially of what we're going to be covering here in the beginner's track, here's that right now. Pretty much this beginner's track, we run 3 different tracks every quarter. There's the beginners, there's the advanced, and then there's the projects. And so essentially our idea here is you do the beginners, and then you can hop over to the advanced and learn the big boy stuff. And then you actually apply that in the projects, That's pretty much it for the formalities. But yeah, if you guys have like any questions or anything throughout the presentation, feel free to like raise your hand or just like shout as loud as you can. One of the two will work. I think one of them's funnier though. So whatever floats your boat, you know. But before we dive into like all this like technical machine learning and whatever talk, just a heads up, it may be a little much. We try to like make it as straightforward as we can, but the reality is like machine learning AI, it's a pretty complex topic. So sometimes like you may need a little bit of time to digest it. The reality is like if machine learning and AI was so easy to learn, everyone would already be doing it, right? And that's why we have this club, so like we can maybe get a step closer to that. But yeah, don't panic. We're gonna hold your hand. It'll be okay. All right. Let's talk about machine learning now. Let's do a little quick crash course here. So first things first, what does it do? What is it, right? Ignoring the big elephant in the room here in that background there, ChatGPT, right? Machine learning and AI, it's pretty much everywhere in our world right now. Like anything that relates to automation, anything that relates to technology and like making technology more efficient, you can pretty much at this day and age, like all point it to this idea of machine learning and AI. So one case point here, right, is this idea of computer vision, right? Let's say I have a machine and that machine can see things, right? What can I do? One application of that is self-driving cars, for instance, right? So here's the idea, right? We're humans, right? We drive cars, right? And we have logic to drive these cars, right? We know the traffic laws, we can read the signs, right? But what if we had the car do that, right? What if we like put a brain in this car, right? If we taught a car like how to like stay in the lane, how to merge, how to like follow the traffic laws, how to read the traffic signs, like, do we really even need people driving, right? Like, can't we just like have the car drive themselves, right? Like, why do we need people for all this, right? We can technically automate that utilizing machine learning and AI, right? The reality though is you need to build it, right? The car's not going to drive itself, right? So that's why we're here to maybe break down an approach and actually build things that can help you automate like that, right? But anyways, big picture stuff out of the way. I keep forgetting that there's two laptops up here. Let's talk about machine learning and AI. This is going to be a lot of terminology right here. It's going to get a little groggy. Feel free to take notes or whatever. You don't really have to, though. We'll post the slides anyway.
You can find them all in the asset cluster, hopefully listed up here.
Yeah, the cluster's over there. To you people over on Zoom, good luck. Yeah. Going to be a lot of terminology I'm about to throw at you. TBH is going to be a little, it's like 3 terms, but it's going to be a little groggy. I swear our meetings are going to be a lot more interesting than this first 30 minutes right here. You're going to be working with stuff at the end of this meeting, okay? Just stick with me here, right? But machine learning and AI, I feel like when you hear these terms all the time, right? But like, you may think like you can utilize AI and machine learning pretty interchangeably, but they're actually 2 pretty fundamentally different concepts. So let's define them really quickly right now, right? So the idea with artificial intelligence, right, is essentially artificial intelligence is the idea that we can make machines or programs do things that we only expect humans are able to do, really complex things. That's the idea of artificial intelligence. Computers doing really complex things that we only associate with humans, right? So that can be decision making, that can be like vision, like senses, you know. These are things that we can comprehend that we don't think other things can comprehend, right? But if, for instance, we wrote a program that saw things, right? That's an example of artificial intelligence, something really complex, right? The difference, though, is machine learning is a subset of artificial intelligence, right? So artificial intelligence, you got like programs that can do super complex things, right? Things that we can do, right? The idea with machine learning is machine learning essentially, let's say like you code your program to do one thing, the machine learning program can maybe utilize your program and do things that weren't explicitly hard-coded in your program. AKA, machine learning is essentially how you do logic in your program, right? You give your program maybe a set of rules to follow, and then it just does things based on those rules that you didn't tell it to, right? Maybe you're telling it like, oh, here are the rules for checkers, right? And then your program does all the moves. Did you code those moves into the program? No, the program did that all by itself, right? So that is machine learning, right? And the power here is you take your artificial intelligence, you take your machine learning, you like fuse them together, and then you get like some crazy, crazy technology, the stuff that you see today, right? But those are pretty much the definitions, right? We're pretty clear on that. Thumbs up. Yeah, cool. Okay, so again, these are pretty high level concepts, right? Like we're going to be talking about how to like build stuff, how to do things, right? What are the things we need to like do stuff? One of those things is called a model. What is a model? Don't overthink it. It's pretty straightforward. Essentially, it's something that takes an input. It's like 3 phases, right? First, you take in your input, then you do some magic processing, and then like at the end, you throw out some output, right? So for instance, right, let's say that we're a model, right? Not that kind of model, not yet at least, right? But like, let's say that we're a computer model, right? Someone hands us a photo. They're like, I don't know if this is a cat or a dog. Tell me if this is a cat or a dog, right? We take this photo, right? That's our input, right? We're looking at it, right? We're doing our magic in our brain. We're identifying whether this is a cat or a dog, right? We look at this, we're like, okay, this has got to be a cat, right? So we hand the photo back, we're like, this is a cat, right? That's input, processing, output right there. Fair enough? Another idea is Google Translate, right? We type in an English sentence, right? That's the input, right? Google does whatever the heck Google does, collect your data, whatever, right? It collects your data, whatever. That's the processing. And then it outputs, like, let's say I'm translating to French, right? It outputs the French translation, right? That's another example of a model. Like, it's really that straightforward. Like, don't overthink it. Input, processing, output, right? And essentially, the way that we can build better models are basically things that can, or models that can output things that are actually useful to us. The way that we build those kind of models is through something called training, aka we tailor our inputs really well, and then we tailor our outputs. We take a look at what this model outputs to us. We're like, is this what we want or is this not what we want? And then we keep regurgitating, we keep trying, we keep essentially experimenting with this model here until we get something that we actually want, right? Because the model only does things based on what we give it, right? So we just keep giving it better stuff, and it hopefully, right, not all the time, it gives us better output. That's the idea of training, right? And generally when we're working with models, there's generally 2 different categories, right? Based on the type of data that you're working with, right? The first type of model is the continuous model, right? So let's say you're working with things with like infinitesimal precision, right? Let's say like you're working, your data that you input is like a weight, or maybe it's like a temperature, right? Or maybe it's like your altitude, like above sea level or something, right? You can have infinitesimal amounts of precision, right? You can do like a kabillion decimals, right? You can just keep getting more and more precise, right? The data is not necessarily black or white, I guess, right? When we have data that just can get more and more precise as our input, when we input that into our model, that model is considered continuous, all right? On the contrary, though, is this idea called a categorical model, right? So let's say our model like doesn't work with like data, right? Let's say our model, we're trying to build our model to classify things, right? Let's say our model, like that example earlier, right? Let's say our model tries to identify what's a cat and what's a dog, right? Maybe one way our model differentiates between a cat and a dog is by finding traits, right? Maybe a cat has like sharper claws, maybe a dog like barks, right? These are considered when a model breaks down its data based on traits, right? When it like, you give it a lot of data and it just separates it into like different categories based on certain criteria. That is what is considered categorical, right? You get a piece of data and you look at your data, you're like, okay, it's either this or it's equal to either that, right? If that makes sense. So for instance, with a continuous model, right, you get a temperature, you're like, okay, this is hot, this is warm, this is cold, right? You get your categorical model, right? You get a photo of a cat or a dog, you look, you're like, okay, it's got sharp claws, it's got really pointy ears, I think it's a cat, right? You analyze it differently, right? Continuous, maybe like you say, like if it's within this range, right, then it's like a warm temperature. But like categorical, maybe like you say like, oh, this it's like 80% shot it's a cat, right? And then you roll a dice and then you pray, you know? Does that make sense? Cool. All right. Anyways, a lot of vocab there. Let's talk about general concepts now. How do you build a model, right? Generally, building a model is broken down into 3 steps. First things first, you get a lot of data. Like when you think about a lot of data, like do like 10 times that. We're talking a lot of data here, right? And you get all this data, you really hone it, you make it really fancy data, give it a lot of information in your data, and you throw it all in this model, right? AKA the training, right? You throw all this data in the model, right? And then like you double check whether your model's like outputting things correctly or not. You really work on making your model like do what you want it to do. And then once you think like, okay, my model's good, then you output it. That's this third phase here, the model. You use it in the real world, right? It's not that's really it. Like it's not don't overthink it. That's literally it. There's 3 phases. You start with your data, you use that data to build your model, and then you use your model. Good? Okay. Oh yeah, but these slides will be posted. Don't worry, y'all. But anyways, given that, you're probably thinking like, oh, like there's so many different kinds of data, right? Like, how come like there's only like, oh, how come there's like the categorical and like the other one? You probably forgot the term by now. Whatever, it's all good. It's okay. But turns out there's different kinds of machine learning models, and I know I only said I was going to throw 3 terms at you. Those are the 3 important terms. I'm about to throw 4 more at you. Prepare yourselves. This may be a little boring, but I'm telling you, it gets so much better after this, all right? They just gave me this part, and I have to present it because this is important knowledge for you all, okay? So we're going to do it, all right? Okay, so different types of machine learning models. Essentially, let's break it down like this. Let's start off with supervised learning. So this is a type of model, right? Where essentially, you have your data, right? You already know like what this data means, right? So for instance, like you have data of like the housing market, right? You say like, oh, like in 2008, the housing market, right? Like in January, the prices were really high. In December, the entire housing market imploded and all the houses weren't worth anything, right? You have your data, right? You know the inputs, like you started at this price, you know it ended at this price, right? What supervised learning is you, given all that, you throw all that data in the model and you tell your model, give me a pattern, show me a pattern within this data, essentially, right? So maybe the model will output like, oh, maybe there was like this point in February that caused the entire market to crash, right? The model will give you essentially like different patterns based on your really fancy data, if that makes sense. And then you have this idea called, you have this other form of learning or machine learning models called semi-supervised learning, right? Isn't this just so exciting, guys? All right. Semi-supervised learning, all right? Let's say I have a bunch of data, right? Let's say I have like 1 million photos of cats and dogs, right? And let's say I've only identified 100,000 of those photos. 100,000 of those, I'm like, okay, these are cats and these are dogs, right? But I really don't want to identify the other 900,000 of them, right? That is a lot of work, right? So let's say I throw those 100,000 photos into the model, right? And I tell my model, hey, these are cats, these are dogs, figure it out. I got 900,000 more photos. You tell me if those are cats or dogs, right? Essentially, with semi-supervised learning, your model will take in labeled data, aka cats or dogs, and then given unlabeled data, it'll try to label the unlabeled data, if that makes sense, right? It'll try to like, given random data, it'll try to categorize it based on what it already knows, kind of, okay? And then another type of learning is unsupervised learning, right? Let's say I just have a bunch of data. I have no idea where to begin with this data, right? I can just throw it in a model and I can just pray that the model can figure it out. And the model generally does figure it out, right? It'll figure out a pattern, right? And then maybe we can use that pattern that the model built or like regurgitates to maybe like figure out what all this data means, right? So for instance, an example of unsupervised learning is, let's say like I run a company, there's a lot of customer service complaints, right? And there's a lot of words, a lot of different types of complaints, maybe one person's product arrived broken, maybe like a person died from your product or something, right? Lots of different data, right? You throw all of that into the model and you're like, hey, model, what's wrong with my company, right? And then the model will maybe give you a couple ideas, right? It's not like, I mean, you get out what you put in, right? You don't know, the model doesn't know either, right? It doesn't like work all the time, but it's one application, right? Another application, final one here. I know you guys have made it. I believe in y'all, okay? Reinforcement learning. Can we get some reinforcement learning? Yeah! Reinforcement. Okay. I'm so sorry, y'all. Okay, but reinforcement learning, right? The idea with reinforcement learning is it's really like hands-on with your model, right? So reinforcement learning is essentially your model, rather than like categorizing data, right? You give your model a set of rules, right? You tell your model, okay, like, let's say your model is like identifying trees, right? You tell your model essentially, hey, my definition of a tree is something that has wood, something that has branches, and something that has like leaves on it, right? And then you throw a bunch of data at it, right? And then your model essentially regurgitates what it thinks is a tree, right? And then you look at the data that it outputs, you're like, this is a seahorse, this is not a tree at all. I need to give you more rules to identify trees, essentially, right? The idea with reinforcement learning is you start off with a bunch of rules for your model, you see the output, right? And then like you keep giving it more rules to further hone the output to what you want it to be, right? That's reinforcement learning right there, okay? Any questions at all, or? Yep. Yeah, pretty much. Again, this is all big picture. I mean, you can't like hard code like, hey, like model, like this is a branch, figure it out. But yeah, generally with reinforcement learning, you're working with like general rules, right? With the other models, you're telling the model kind of just sort of figure it out, give me something new, right? But with reinforcement learning, the thing that's different, I guess, is like you already kind of know what you're looking for. It's just you're trying to like maybe like automize it a little, But yeah, yep.
So specifically the difference in reinforcement learning and how it's different from traditional learning is you can kind of think of reinforcement learning as a generalization of traditional machine learning techniques. Like if you're classifying images of like cats and dogs, right? Your data set will stay the same. You finish classifying the thing, your model will not affect what the data set is. You have predetermined the task saying, this is my task, the data set's not going to change. However, with reinforcement learning, say applied to self-driving cars, as you train the model, the car, for example, will make different behaviors as you train a model. And as it makes different behaviors and it sees different things, your data set starts to shift. The term we use is your data distribution is not constant. And because of that reason, we can't just use a lot of like existing techniques that we have for machine learning, because that assumption that the data set's constant is no longer there. And that is also why we have to have extra assumptions to help the model, as you were saying, where like, for example, we have we predetermine like rewards and predetermined rules. Like, I want the car to say stay in the middle of the road, because it is to the point where the problem is so difficult that we need to help the learning process a little bit with even more predetermined assumptions. Does that make sense? Yeah.
That's our president, Jordan. He does research in this. He's probably more correct on this, all right? So I listen to him. Okay. Yep. You input those rules, not the model. The model is just like you tell it the rules, it goes to work, it comes home, and then you complain. That's reinforcement learning. Okay. Lot of vocab, disgusting, no more. Okay, let's dive into KNNs. All right, KNNs. This is where things get interesting. All right, let's say you're walking in North Campus, right? You're having a lovely stroll, right? You're walking through the sculpture garden. Wow, these sculptures, they're so beautiful, right? And then you hear some rustling in the bushes, right? Oh no, what is that? Something jumps at you from the bushes, right? Oh my God, it's this thing. You're like, oh shoot. And then you're like, wait, what is this? Is this a cat or like a dog? Is this like some like cat dog thing, right? Like here's the thing, right? Like if you look at this image, like is this thing gonna purr? Is this thing gonna bark? All right. And now you're standing in the sculpture garden. You got like an ethical crisis, right? What is a cat? What is a dog? Where's the line? How do you identify things? Why am I here? This is the idea of KNNs, right? How do you identify things? So I lied to you all again. More terminology coming right back at you, but I'm telling you, this one, it's the last one. Trust me. Okay. So essentially, the idea with KNNs, right? Like I said earlier, you have this idea of cats and dogs, right? And this sort of line, right? How do you figure out whether a thing is a cat or a dog, right? Let's say someone gives you 1 million photos of cats and dogs, right? How do you separate them? Okay. One approach is by looking, like I said a little earlier, at features, right? So for instance, like maybe we say like, okay, like cats have really sharp claws. Dogs have really dull claws, right? We can utilize that feature to differentiate these 1 million photos between cats and dogs, right? That is an example of a feature, okay? And then there's this, once we confirm essentially that, okay, out of these 1 million photos, this one photo is a dog, then we label that data. That is the second bullet point here, right? So you have 1 million pieces of data, right? That you separate them using the features, right? And then you label them once you confirm, like, I think this is a dog. You label that as a dog, right? And then once you do that, then you can begin throwing into the model, doing your magic, whatever you want to do, right? So just to clarify, features help separate your data, right? Dogs bark, cats meow. We use that to separate our data, right? And then after that, once we've confirmed this is a dog, this is a cat, then we begin labeling them. We're like, okay, this is a cat. This is our model for what a cat is, okay? All right, so yeah, cats and dogs. Can I get like maybe an idea for like maybe other traits of cats and dogs in the room? Anyone? Yep.
I guess it's like
Them-
cat's eyes, they reflect more lights.
That's true.
It doesn't really, like, not all pictures reflect that feature though.
That's fair. That's an idea. Yes.
That's too bad. Should I give it
No, that's good. No, like, I don't know. It's really open room, man. Like, there's no right or, I mean, I was about to say there's no right or wrong answer, but like, I can't be saying that, you know? You can't be doing that. Yep. Yeah, different facial features. That's definitely one. For the sake of time, let's just like spoil them all, I guess. Here are some traits. I've talked about them previously. I think they're pretty clear. We're humans, right? We know what cats and dogs are, right? We know that, right? Computers, though, they see cats and dogs, they get that ethical crisis, right? This is why we need those features, okay?
The cat is plugged in. We just figured it out.
The cat's plugged in? Sure. So this, okay, unrelated to the lesson, this is called data noise, okay? This is when you got bad data, right? We don't want that, okay? Good point, great point. Thank you for sharing that. But essentially the idea now is like, we divided our data, right? We said, these are cats, these are dogs, right? What we can do now, right, is we know what our cats are, we know what our dogs are, right? We plot it on a graph, right? Where the axis is like the feature of one thing, maybe a cat, and the other axis is the feature of a dog, right? So in this case, our y-axis is the sharpness of our claws, right? Where the higher you are on y, the more likely it is you're a cat, right? And then our x-axis is the length of our ears, right? Where the higher our x is, the more likely it is you're a dog, right? So this is sort of a loaded question right now, right? So let's say like, given this graph, right? We got a whole bunch of points of like, okay, these points are cats, these points are dogs. What we can kind of do is we throw a random point on the graph, right? And then based on the data that we've confirmed already, right? We can say, okay, is this closer to being a cat or closer to being a dog, right? So let's say I throw a random dart at this graph here, and let's say that dart is under this triangle, and I should have moved this somewhere else because this is kind of loaded. But does anyone want to guess if the dart under this triangle is a cat or a dog? Even though you can't really tell on this graph, flip a coin, place a bet, cat or dog, anyone? Cat? Man, y'all should get a lottery ticket or something. Yeah, it's a cat. We got a cat under here. Good job, y'all. You won $1 million. Yeah, that's an example of essentially why we categorize data, right? So we know what our cats are, we know what our dogs are. So now we just have a random piece of data. Now we can figure out what's more likely to be a cat or a dog based on this graph, right? And that's the idea of a KNN. Venkat will dive into it a little deeper. But yeah, so if you remove this idea of cats and dogs now, just break it down into like something more simpler, right? You have class A and you have class B, and you're trying to identify class A and class B. You can utilize the same graph idea, right? Where maybe like you plot all these things that you've confirmed is class A, and you plot all these things that you confirmed are class B, right? And then if you throw a random dart on that graph, right, then you can figure out maybe what it is more likely to be, if that makes sense, right? Same idea. And then you can utilize this graph idea anywhere. And then you can identify anything. Crazy, huh? That's KNNs. But we're going to dive into it a little deeper in a little bit. And also, notice that this is categorical. This is a categorical model right here that we built here with this graph, right? We're working with features and traits, not temperatures and numbers, okay? These are like, it's either you got long nails or you don't, you know, things like that, okay? But yeah, that's it for my little introduction here. We're gonna do like maybe like a
We'll take like a 5-minute break and then
Yeah.
we'll resume back.
5-minute break. Yeah.
All right. We're gonna go ahead and get started with the second half of the portion, and we're just gonna formalize everything we talked about with KNNs so far. All right, cool. So we have said that we have gotten the k nearest points. So now, how do we want to use these points in order to create a classification? So when we have, like, let's say, a list of data, and we want to figure out what is the most common occurrence in that data. What do we call that? It's on the slides, but any volunteers? It's on the slides, guys. The mode. And so basically, if we have a bunch of points near a data point we're trying to classify, and we gather all of that, and then we go, oh, we see that a lot of the classifications near this are a cat. So the mode of this data is the cat. We can classify our point as a cat, right? Does that make sense? So with KNNs, we're looking at what is the classification of things around this data point. And so basically the entire next portion of this is on how we formally define closeness, how do we pick these points and things like that. Okay. Wrong computer. So KNNs have this term, k nearest neighbors. And so the neighbors are the points that are closest to it. And so the first question we're going to ask is, how do we pick good neighbors? So this slide is saying that a good neighbor is a person that doesn't have a Wi-Fi password. And if you live in the apartments, which if you get the chance to, you will actually find that this is true because the internet does go down. And I would love to leech off of some other people's internet. But not everybody's a good neighbor, unfortunately. All right. So more mathematically speaking, when we have all of these data points, they live in a two-dimensional space. And within this two-dimensional space, we can look at how close these data points are to each other by using the Euclidean distance. And so for 2 points, x1, y1, x2, y2, this is the Euclidean distance formula. So square root of the difference between the x terms squared plus the difference in the y terms squared. One note, right? This does also generalize to things that are not two-dimensional, right? So if we're working in a three-dimensional space, we just tack on the z terms here. So this does expand to larger dimensions, not necessarily just where we're having like two classification points. All right, so we have decided neighbors are points that are closest to each other. And then now how do we define nearest? Nearest is quite literally which ones minimize the Euclidean distance. So we're literally choosing the k closest points. Do we have any questions so far on like the premise of using the Euclidean distance to select points and things like that? All right, cool. So now the one term that is not apparently obvious in this is this random k we have at the beginning. K is something we call a hyperparameter. And a hyperparameter in machine learning is a parameter that we, the people who are building the model, can select and fine tune depending on our data. So, for example, in one data set, we may say we only want to look at the 10 closest points. In maybe a larger data set where we have a lot more data, we'll be like, let's look at the closest 30 data points. And so this k value can affect our classification. And so one of the important things is how do we choose this k value to get a good classification? So assume that we can select k. And so this is the general algorithm we're going to be working with. So we have one point, P, and then we want to compute the distance between this point P to all of the other points in our data set, right? Then we're going to go ahead and sort this data set based on the minimum Euclidean distance. So the top entries, once we sort it, are going to be the closest to this point P. Then we select the first k entries in this sorted list, and then we find the mode of that. So that's just a very algorithmic way of saying choose the k closest points and find out which classification is occurring the most. Okay, so this is a great example to talk about why choosing the k value is so important. But in this case, if we choose k equals 3, can anybody tell me what the classification of that question mark will be? Yes, that is correct because we have two triangles, one red star. But now, if we choose k equals 7, what is our classification? So depending on our k value, our classification is going to change. So how do we actually determine this k value? We would really want to look at what the question mark is, and then we would make a judgment call, right? So in this case, if the question mark was a triangle, k equals 3 would be better. If it was a star, k equals 7 would be better. But it's not really that feasible to do this for every single data point, for every predictor we're trying to make, and then change our k value, because that would just not be a good model if we had to keep changing our k value. We want something where we have a k value that generalizes to our data. Okay. And so once again, this slide is just going over that general algorithm, right? Saying, let's compute the distance between our point P to all of these other points, and then pick the k closest ones. Okay. So we will do a quick quiz. We have 2 questions like this in this workshop, but we are trying to classify the green data point, k equals 3. What are we going to classify it as? Red. All right, perfect. That was actually the fastest response we've gotten so far in any of the workshops we've done. But yeah, that was awesome. Okay, cool. So now we're going to choose how to fit this hyperparameter k. And this will be more simpler than you think. So as we went over, k equals 3, we may get the right classification, and then k equals 7, we don't get the right classification. So is there any general rule that we can use to choose this factor of k? Ideally, as I said, we want to try both, see which one gives a higher accuracy based on our testing data and validation data, but that's not always really feasible when we start to go into the real world. So there are 2 scenarios here. We can pick a really small k value, or we can pick a really large k value. And so there are 2 situations that are up here. So if we pick a very small k value, what happens? What are things that can go wrong if our k value is really small? So say we're only looking at like 2 data points, 2 or 3 data points that are next to this in like 1,000 size data set. We have a very small k value. Any guesses on why we may not want a very small k value.
Those two could maybe be like outliers that are separate from the actual like representation.
Exactly. So for example, imagine we have divided our, we have two planes. One is red, one is blue. The blue one has like a couple red dots here and there. And if we place a new blue dot very close to these other red dots, and we only choose k equals 2, even though it's in this entire blue region, we will still classify it as a red dot. So choosing something that's very small, we don't really account for a more wider array. And so we may be a little bit more biased. And so outliers are a very big issue in that case. Now, somebody may suggest, okay, so if we want to avoid outliers, let's choose a really large k value. And the easiest way to demonstrate an issue with this is what happens if we choose a k value that is equal to the total size of our data set. So our k value is all of the points in our data set. Do we have any ideas? Yeah.
It's like the determination of each data points are all going to be the same because they include all of it.
Exactly. So our data set is fixed. And that means the mode of this data set is pre-calculated. It's predetermined. Basically, whichever element is occurring the most will always be our classification. So now we kind of see an issue between can't make it too small, we can't go too large either. So how do we really choose this? The thumb rule is k equals the square root of n, where n is the size of our data set. And so we won't get into exactly why this is. It's more of like it's come from trial and error and things like that, but this should give you some general intuition. If you think about the square root function, what's going on? Small data set points, we will be more likely to consider the entire data set because anyways, it's so small. But for a very large number, say like 100, we're only going to be looking at the 10 closest data points, not 50, not 20. Because we found that maybe choosing 50 data points is too large when we only have 100. But something like 2 data points, 3 data points gets affected by outliers. So hopefully, if you kind of think about the square root function, you kind of see this idea that as the data set is increasing, we don't necessarily want a linear scale. Because at some point, even if we have like 1,000 data points, choosing like 200 closest things is just, it still is going to be a little too generalized for us. So that is kind of maybe a little bit of a visual intuition on why we want square root of n. Now, there's also another really neat trick that we like to do, and that is we always pick an odd number for k. And that is because we don't want to tie. So if you pick any even number, the chance that half of them is going to be one classification and the other half is going to be another classification, it's a possibility. And then we have to design something to figure out that tie, maybe flip a coin there, whatever. And we don't want to do that. So instead, what we do is we say we're going to have an odd number, and that guarantees always that our classification is going to be one thing. We will never have any ties. Now, the thing of k equals square root of n is just a starting point. And so if you remember a couple slides ago, we talked about how you want to really see whether that k value is performing well with your accuracy or not too great. And so this is a starting point. You go ahead and you look at your validation results. How is this model performing? Maybe square root of n is not the best number to pick, something smaller, something higher. And so we use this as a starting point, and then we can branch off from that starting point to really get a better k value. And that is just trying these different values to see what gives you the best result. Any questions so far on like choosing the k value, the reasoning behind it? Yeah. So that is one idea, right? We can weight it depending on the closest to the point. But again, that entire idea of outliers becomes an issue there. I'm not too sure about the theory behind that. It's something we can look into. I don't know if Jordan knows weighting data points.
Yeah, that's something that people commonly do as well. It's like they will like weigh it to say like the reciprocal of the distance, for example. So like the closest points are more influential than the points which are further away. That is something that people do.
Yeah, a lot of what we do in machine learning, you can think of it as like common sense, right? Like maybe things are closer, we're going to weight it higher, and we try and see how those techniques function. Yeah. I mean, this will still work for multi-class classifications. So imagine instead of just dealing with like green triangles and red stars, we had green triangles, red stars, and blue squares. The same theory still here just applies, right? We just have like another entry that we have to think about that could possibly be our mode of what we are picking. Does that make sense? Okay. Yeah.
You pick like a odd number, let's say you pick 9, but then like 3 red, 3 blue, 3 green together, then you
Yes. So that does become an issue when we choose more when we have more categories, but there will be a number such as there will be some sort of split like 7 where that will not be an issue. And so as a thumb rule, if we're just doing categorizing 2 variables, we want to pick an odd number. Any other questions? Yeah.
that situation, would you do like odd, like the number and just trying to get like a remainder, and that's like there.
Mod the number.
Not which number?
Like the number that they're saying, like however many categories you
You're still picking a mode because you're trying to find the current like you look at all the KNNs neighborhoods, you're saying which class is the one that's occurring the most frequently. That's the mode, right? Like modulos, I don't think really applies here.
There is a slight issue with modulos, and that is like, for example, if we were dealing with maybe a number like 7, and we have 3 categories, 7 mod 3 is 2, right? And so we're not really getting, like, we would not want to just pick 2 data points in that case per se, right?
Oh, I just like it, in that case, like you have a remainder about.
Mhm.
Then you know it's like a good number there.
Yeah.
They're like,
Yeah, that is one way. We can look the modulus of that to determine if it's 1, and then it's a good number. You are right in saying that we can use the modulo to determine if this number will have some sort of permutation where 2 categories will tie with each other. Yes.
would it be effective to have some lead go through multiple different values?
Yes. So that is actually something we do in machine learning. The part where we use k equals square root of n is the starting point for that loop. So one example is we may want to start at k equals square root n and then branch out from there. So instead of starting at like 1, because we maybe for high dimensional, not high dimensional, but where you have a lot of data that may not be too great, it's just like a starting point. And there is a technique called k cross-fold validation, in which we do something very similar to that. All right. Yeah.
Just out of curiosity, so when you have an outlier, is it better to give it a light weight or is it better to just classify it in different fields?
So when you say if you have an outlier,
Yeah, for example, like there's a graph like red circles
Mhm.
and blue squares, and there happens to be a red circle right here.
Mhm.
So is it, in that case, is it better like with this data, if you just classify that as a different category or you just get that data very lightly?
so right now, the way we're weighting our data is based on the distance to a new data point, if that makes sense. So all of this is just in our data set. And now we're taking in a new data point and we want to classify it. And so then the real question in a scenario like that becomes is like, how do we figure out those weights? And in your case, like if we just had like a single red dot and then like a bunch of blue ones, the idea is when we're taking the mode, we're able to ignore that red dot. I don't know if that's answering your question, but
No, I was thinking about more of having a set weight for each data point rather than like recalculating the weight like after having.
so in terms of determining like the weight of a data point, we usually would like to do that with respect to the data point we're trying to classify. So for example, if we said like red dots, like half of these red dots have this sort of weight, the other blue dots have this sort of weight, we may want to change those weights based on the data point we're trying to classify. And so there maybe that could work. I'm not too sure, but yeah. I don't think it's done in practice. So you are correct in that if we have n by n data points, then we can classify each value by assigning, let's say 0 represents category 1 represents category 2 represents category 2, et cetera, et cetera. In terms of assigning a weight, like if you want to weight the matrix, we could create another n by n matrix, and each entry in that n by n matrix will be the weight of the corresponding entry in our categorical, the matrix that classifies all the categories. So if we have two n by n matrices, we can. So matrix multiplication will not necessarily work here because we need to choose the k closest points.
Yeah, that's why.
So go ahead, Jordan.
So I think you're like slightly confusing like neural networks, which is what we're going to talk about later, and also in abstract if you're interested in that. That's like a slightly different thing. When we say like weighing it here, like there's obviously like implementations of K-means clustering that uses like vectors and things like to make it faster. But when we say weighting them, that's something that will kind of recalculate on every single new data point, because we're, you know, when we have a data point, the distance from that data point to every single other data point, that's new, right? Because like you never know what your input is going to be. And because it's new, we have to then, you know, do all that recalculation and do all that reweighting. You can use a vector operation to do this. It will make it faster to parallelize things, if you will. But you know, like we don't have matrices here necessarily. You know, that's a different thing. That's neural networks, in case you're wondering. Yeah.
So how do you kind of do different categories?
In this particular, like for KNNs, like if you were to say actually implement this in Python, basically you'll like have like two lists. The first list is like, you know, a list of all the positions of your inputs values, and the second list is maybe like the label, right? Like the say class 1 will be label 0, class 2 will be label 1, 0 indexing, right? And then you will have that, you know, paired up information to be like, oh, this point here is this class, this point here is this class, and just write a bunch of formats to try to figure out which one's the most and stuff like that. Does that make sense?
But like the idea would be to like lay it out, draw out all the points, and then have the resistance.
Plotting out the points is a way to help us visualize it, right? But when you're actually implementing the algorithm, you're really just looping through all the points, calculating all the distances, saying what are the top k distances and what are the corresponding points. Okay, got the corresponding points, we find their corresponding labels. What's the most common label in this top k? That's, yeah. So again, like the thing about machine learning is that you will see that implementation is often a little bit removed from the visualization, because computers are able to do things like much quicker instead of like us looking at a certain things, for example.
So like, if you want to keep track of a feature, you only have one feature, whether it has this feature or not, or do you have like in between? Is like.
So I think like the best way to think about this is if we have our input data, we can just think of this as like a large list, and each entry in the list will contain two values, right? The classification and let's say like the location, right? So if we're just working with 2 dimensions here, this would be like an X and Y value.
Yeah. And when you're referring to features, specifically for KNNs, we'd like to work with continuous features. So for example, your X coordinate will represent, say, the length of the flower petal. And your Y coordinate may refer to the length of the flower stem, right? If you were to say classifying types of flowers. So, and you can imagine how this can be extended to higher dimensions, 3 dimensions, 4 dimensions. You're just doing this, you know, you're creating distance calculation in a much higher space, which it's difficult to visualize, but the math is just you square all the, you know, the distances thing, and you take square roots, you know, how you do distances in 2D, expand into multiple dimensions.
Yeah, that's why I'm asking like how do you weight each category if you really want to.
If you really want to, you basically take the distance and you do like 1 over the distance. So the further the distance, the less it is. The closer the distance, the bigger that weighting is. Does that make sense?
Yeah.
Like it's just one of the methods. Yeah, people do a lot of different things.
You only keep like your data in one single, like, I don't know, 1 by n.
Yeah.
Okay.
Yeah. Again, that's all implementation details and it differs depending on how you implement it. Right. So
The important thing is we can't really pre-calculate these weights because the distance is dependent on the point we're looking at. So for example, if we have like 5 different points that are all the same distance from the point we're trying to classify, we may weight those points differently. We may want to weight them equally. But versus if we have 5 different points that are all 5 different distances and we're classifying it, we're weighting what is closer a little bit more, then we have to change how we compute our weights. So this notion of like predefining the weights for each value doesn't really work when we're trying to classify a new data point.
yeah, like KNNs is a special case in machine learning where like our ideal machine learning is that, oh, you first train the model, then you just really quickly be able to test it. But the thing about KNNs is training time is constant, right? You store your inputs or like you store your data. That's all you do. And when you're testing it, or when you're doing inference, or you're passing an input, that's where most of the calculation happens, which is going to be different than what we're going to be looking at in the future with linear regression, logistic regression. But that's kind of how KNNs work.
Determined by the.
Yes.
Okay.
Any other questions? So, this is this second question. If there are 170 data points in our data set, which K value do we want to pick? 13. Perfect. Anybody want to explain their reasoning? Yes. And 13 is also an odd number. Cool. So Jordan briefly started talking about this, but KNNs don't really seem to have any training. We simply are just storing all of our data. And then when we get a new point, we're trying to classify this by computing all of the distances. And so we're not really training any weights here or anything like that. Instead, what we're doing is we are doing a form of lazy training, right? So all the computation we're doing is when we're trying to classify a point. So KNNs are a type of lazy learning algorithm. The next couple algorithms we're going to cover in future workshops are going to be something called an eager learning algorithm, where we're trying to figure out these weights, train the model, and then actually predict. Here, we just have a data set and we're predicting something based on a K value. Okay. We're running a little short on time, so we will just go over the pros and cons really quickly. So pros of KNNs: no training means they're very fast and they're pretty easy to compute. They work pretty well for small data sets, but when we say they don't work, so if they work well for small data sets, likelihood is they don't really scale that well for larger data sets. And part of that is something called the curse of dimensionality. Basically, when we start working in higher dimensions, distances actually get longer. And so then a concept of weighting actually will help. But that idea of distances elongating, and then it kind of messes with our intuition on defining what is the closest. Okay, so we will do a quick case study here. And so this is meant to just run through how a KNN will work on a sample data set. So we have 2 features, X and Y, and each sample is a 0 or a 1. And our goal will be to classify a new point P. And here is our P value, 57 and 170. And so we want to figure out whether this is a 0 or a 1. As we said before, to figure out the distance, we're going to use the Euclidean distance. So here's what's going to happen. Every time, we're going to go through all of the data in our data set, and we're going to compute the Euclidean distance. And that is basically the distance value you see over here. Now, there is one important step that is actually missing from these slides right now, and that is you have to sort it. Just one second. And because if you don't sort it and you just pick the K ones, those are not going to be the K nearest ones. So it does need to be sorted after you compute all of the distances. Yeah.
Just a quick question. So if you don't know the K value, so do you train for the K value, like how do you figure out the optimal K value?
So as we said, the K value, we basically, what happens is we're like, K equals the square root of n. So we have this base K value. Let's see how it performs on a bunch of data we've not seen that is in our data set. Suppose it's not doing well, we may try and increase our K value. And then we look at that. Is that working well? Is it not working well? If it works well, we found a good K value, we're great. If not, we're going to try and find a different K value.
You can imagine how like now when we search through all the possible k values from 1 to the total number of data points, or from 1 to the square root of k, or square root of the total number of data points, for example, and just pick the best.
Kind of training tool. Like you can have a training data set to find the optimal k value, then you can apply to like a larger data set.
Yes, that is. So generally when we talk about training, we're really talking about like crafting weights that'll predict it. So we do train to figure out our hyperparameters, which is what k is. It's not really a weight. And so that's just a very slight distinction,
Yeah.
but yes.
Okay.
So really quickly here, we have 9 data points. Square root of 9 is 3. So k equals 3 is what we're going to use as our classification. We find the top k values. And then in this case, our label would be 1. We look at the top 3 values. We have 1, 0, 1. The mode of those is 1. And so that is KNNs on like an actual very small data set. And this is how it works in practice as well. So this is a quick recap. We're given a data set and a new point to classify. We compute the distance, and then we sort, and then we take the top k values and find the mode of those values. There we go. So this is a fun topic, normalization. So this is a data set that we have, and it is basically just a vertical line with a bunch of colored circles. Now, do you think KNNs would really work that well in a data set like this? Not really. The distance between these points is not that great. And so we really don't get a good idea about the categories of these. So one strategy we would like to use is we would like to normalize this data. And so basically, this is what normalization is. F is one of our features. U is the mean of all of the features. And we divide it by the standard deviation. And basically, the entire point of normalization is we go from what is on the left to what is on the right. And we can immediately see that what is on the right will be much more nicer to classify and work with. So that is why we would like to normalize our data. All right. Cool. So we've been trying something new for the past couple of workshops where we like to do an ethics portion at the end of each of the workshops just to talk about some issues, current issues and issues that have happened before, and maybe how the model we discussed relates to some of these issues. Maybe not directly, but the same pitfalls exist within these models. So we don't need to know that for this one. So ethics. So in KNNs, we're using this data set and we're classifying based on its nearest neighbors. And so one really basic idea here is, what if our data set is biased? That means our classification is going to be biased. And so one of the most important things when we're talking about KNNs is that our data is representative of the entire population. There is also another issue in that statement, and that is data inherently within our population can also be biased. And so we do need to account for things like that. And there are 2 real-world examples. So Compass was an algorithm that was used to determine if a defendant would be rearrested in the future. And this was actually used in certain court cases to determine the length of a sentence of a criminal. And it was found that this algorithm was biased against people of color. So it classified people of color to be more often repeat offenders than people of different races. But what actually happened is that the people of color, they were actually not repeat offenders. And the people who were actually let go ended up becoming repeat offenders. And so now we're seeing how this bias is actually affecting people, and they're getting thrown in jail for more time than what should be happening because an algorithm has all of this inherent bias. Another more recent one, probably around 2018, is Amazon used a resume screening algorithm to filter a bunch of resumes for their open roles. And they looked at hiring data, Amazon's hiring data for 10 years. And a lot of Amazon's hiring data was very male dominated. And so this algorithm that they used just discriminated against females, quite literally. So there were a couple of words that it specifically liked, and disliked. And so here are examples of rewarded words. So words that the algorithm thought were good and, past the resume screen. Hardworking, fraternity, engineer, director, and salesman. So, okay, maybe not too bad. And then here are the penalized words that Amazon had. Hobbies. So no hobbies on your resume. Member. Okay, so you can't be a member. Scripps College. Does anybody know Scripps College? It's a women's college. It's a liberal arts women's college. And so it's right there. Fired. Penalized word. Okay, sure. And then Society of Women Engineers. So it's safe to say they did scrap this algorithm. But as we said, the issue there was they were training on their own data for 10 years, which everybody in the company at the time, majority of them were males. So, and hopefully we can see an issue with KNNs in this case where we're looking at the data we have. So if the people, our neighbors, are biased, our classification will also be biased. So that's something, we would like you guys to think about when you guys go and use these models. What are the biases that your models will have? How can you maybe fix these biases? And notingly, there will always be some inherent bias in your models. We do not have a game, but we will be going on to the Python portion. We'll maybe take like a 2-minute break, and then Gregor will go through all of the coding demos.
All right, everyone had a chance to fill that out? Jordan's gonna work on troubleshooting that for you. Okay, so it does work. All right, we're good. Cool. So if you went to our first workshop, the joint kind of welcome day, we discussed a little bit about Python. Can anyone here raise their hand if they've worked in Python before, if they have experience in it? Okay, great. We're skipping all the intro stuff. You guys know what variables are. You guys know how arithmetic works, all that. You're good. Cool. Everyone good with that? Awesome. So we're going to be using Google Colab notebooks. These are online Python notebooks that come with environments pre-installed and give you access to Google compute power. So if you want to be training for long-term competitions or just training your own neural networks, this is a great option. So other than that, if you want to run stuff on your own laptop, you can use something called Anaconda, which allows you to install packages relatively efficiently and also move environments around very effectively. So if you have multiple computers or if you're training in a network, you could simply take the environment files from your Anaconda distro on your laptop and move it to another computer. So this is not necessarily applicable to ours. We are going to be doing more than just an intro to Python. So yeah, if you click on the top link, that will be the code along version of this demo. Whereas if you click on the top one, you just want to see the end, see how it works. Just go there. We'll get through the entire code real quick.
What's the one that's code along? The top one's code along.
Top one's code along. Bottom one is completed if you just want to take a look at what the code's going to do. Cool.
And if you go to the cluster as well, you'll see one of the top or bottom one being linked there as well. So if you're so if you go to the cluster, everything's gonna be there. And when this is all done, the recording of this whole thing will be there as well.
Cool. So first things first, I'm going to kind of take you through how to set up the environments and create your own notebook. So this is a shared notebook that I created today to go through our little crash course on Python and KNNs. Keep going. I'm just zooming in a little bit.
Yeah, you can zoom in and put it on white, but that's more visible.
Cool. So this is Colab. To get started, go to File and save as copy in Drive. This will allow you to create a copy, and now you're going to be running your own code. So because most of you are comfortable with Python, we're going to be skipping through data types and operations in Python. And we're just going to jump straight to KNNs. So first things first, we're going to have to import some packages. NumPy, matplotlib, and sklearn functions are going to be useful for us. The first thing that we would like to do is load the data set in using the built-in load iris function. This is going to load. Once we have run this, this will have loaded the data set into the object iris data. And then from there, if this is your first time in Colab, the way that it operates is essentially you create code blocks or markdown blocks to write out text. So we're going to create a new code block. And just to get more info on the data set that we're using, we're going to print out irisdata.describe. This is a built-in attribute of the data set. So it's going to show us the number of instances, the number of attributes, the attribute information. So this is a collection of flowers. We're given some information about the length and width of their sepal and petals. And from there, we have 3 classes, which are different species of irises. Cool. Any questions? Everyone following along? So to get this, you're going to type out print iris underscore data dot descriptor. I don't know how to pronounce that properly, but
That's what description.
yeah, description. Yeah. So this will contain a ton of information about this data set, including when it was created, what it's focused on, and references within it. This is a built-in data set within sklearn. So this is why this has such a detailed description. Typically, if you're given a data set, you will have to load it yourself using a package called pandas and load it into something called a data frame. And in that case, you're not really going to have as much of a description. Cool. Now that we have the description, we're just going to really quickly look at the features that we're given within the data set. So again, we're going to use print. So again, because this is a built-in data set, this has a lot of built-in functions that we can access using the dot. And this is going to give us our feature names. So we have the sepal length, the sepal width, the petal length, and the petal width. We can also just really quickly check what our targets are called. So we have 3 classes. So from here, what we're going to do is we're going to really quickly separate the data into the data and the target, the features and what we're trying to predict. So before we use train test split, which we imported from scikit-learn, we're just going to really quickly define that x is equal to the iris data's data, and that y is equal to iris data So now that we've done that, we defined 2 different lists and data frames that contain the target as well as the features that we're going to use to predict that. So really quickly, we're going to split this into a train set and a test set using scikit-learn's built-in functions. So what this function is going to do is it's going to split our data set into our train set and our test set. What we passed in with the test size is essentially specifying a fraction of the data set that we'd like reserved for our testing set. So in this case, we're going to be training on 2/3 of our data set and then evaluating our KNN on 1/3 of it. Shuffling will make sure that this is random and can't really be affected by the ordering of the data set. And the random state is basically a seed value. Any questions here? Cool. So from here, we're just going to plot a couple of things. So what this has done is basically just divide up the training set into the 3 categories. So for each different category, we've encoded a 0, a 1, or a 2 to give us the label that we are using. So from here, we're going to use built-in functions from matplotlib. From here, because we're going to be plotting 3 categories, we can copy and paste this down. Excuse me. So as we can kind of see, it's a little zoomed in here. We have a data set with different groups and different classes that can be divided up based on the number of neighbors. So from here, we're going to use scikit-learn's built-in KNN classifier. So quickly fit it on our training data. And then use that quickly fit KNN to predict our based on our X test data. And then we can evaluate that using an accuracy score built into the model. And as you can see, we get 0.98 accuracy. Now, we are a bit over time, so I'm going to spare you guys testing out all the different Ks. But I hope this demo kind of shows you the basics of applying this knowledge and also just how to look at a quick data set that you can see here and evaluating it for how it fits into a K-nearest neighbors classifier.
Anyways, thanks for coming. Next, we're gonna talk about linear regression, and if we can, we will bring it to the platform so we know differently, something like that. We all your feedback, and we do. So, thank you for coming. See you next week.